Hello, advanced mathematicians. Welcome back to Mathematics. Let's start off with a flashback from the last video lesson on trig identities. See if you can prove that tan theta plus cot theta is equal to sec theta times cosec theta. Not a very easy one, but see if you can make some progress. Okay, now I'll run through my solution. So I'm going to start with the left-hand side, which is tan theta plus cot theta. Now, my strategy is, I can see the right-hand side is in terms of sec and cosec, which is 1 over cos and 1 over sine. So a good starting place would be to write tan and cot in terms of sine and cosine, so that we can eventually write them in terms of sec and cosec. Okay, so I'm going to write tan as sine over cos, as we looked at in the last lesson. And because cot is tan upside down, it's tan reciprocal, we can write this as cos theta over sine theta. Okay, now I can see we're trying to end up with one term, so I'm going to need to combine these two fractions. So to combine the fractions, I'm going to multiply the left-hand fraction, top and bottom multiplied by sine theta, and the right-hand fraction multiplied top and bottom by cos theta. So we get sine squared over sine theta cos theta, plus cos squared over cos theta sine theta. Now we have a common denominator, so we can add the numerators. So we get sine squared plus cos squared all over sine theta cos theta. Now, what's another way of writing sine squared plus cos squared? Well, that's our Pythagorean identity. Sine squared plus cos squared is equal to 1. So we have 1 over sine theta cos theta, and 1 over sine theta is cosec theta, and 1 over cos theta is sec theta. So we can rewrite this as sec theta cosec theta, which is the right-hand side, which was the target. So we write equals right-hand side as required. Beautiful. All right, today's lesson is on solving trigonometric equations. It's our last lesson in the trig functions topic, which I think you can say it's been a pretty tough topic. This is also a pretty challenging lesson. Okay, it's one that takes some getting used to. It takes practice. So it's probably going to seem a bit scary at first, but I'll try and go as slow as I can, and we'll do some more practice back in class next week. What a treat. Okay, let's start off with two easier examples just to warm up. So here we are, we have two equations. We are trying to find all solutions in the domain of x as a part of 0 to 360. So this on the end of the question is some new notation that we haven't encountered. This is just saying that x, which is what we're solving for, x is the angle, x is a part of the domain from 0 to 360 degrees. What this really means is just find all the solutions in the first lap of the unit circle. Okay, so this equation right here, cos x equals root 3 on 2. This is an equation that has an infinite number of solutions because the graph of cosine wiggles back and forth forever. Okay, we don't want to sit here and find an infinite number of solutions because we've got more important things to do. So we're just going to find all the solutions from 0 to 360. All right, so here's our approach. Usually the right-hand side of the equation will be a number that we know some information about. So we have cos of an angle is equal to root 3 on 2. As I've said many times in this topic, if you know your exact values from your two magic triangles, these questions become a lot easier. Okay, so the best thing you can do to prepare for this lesson is get your exact values memorized. So if you have them memorized, you know that cos of 30 degrees is equal to root 3 on 2. Okay? What this tells us is that our solution is going to be 30 degrees, and it's going to be 30 degrees in all the quadrants where cosine is giving us a positive answer. Okay? So cosine is positive in the first quadrant and the fourth quadrant. So our solutions to this equation are going to be 30 degrees in quadrant 1 and 30 degrees in quadrant 4. All right, so positive in 1 and 4. So we're going to do 30 degrees in the first quadrant. And in the fourth quadrant, we work back from 360, okay? So 360, take away 30, gets us our second answer of 330. Okay, so if you have your calculator nearby, if you type in cos 30, you'll get the decimal approximation of root 3 on 2. If you also type in cos 330, you're gonna get the exact same answer because they're the same points on the cosine wave. Okay, I'm guessing that may not have made heaps of sense, but once we do a bunch more examples, you'll start to see the pattern and you can follow the steps. Let's have a look at B. We've got sine x is equal to minus 1 over root 2. So first thing is we've got to know our exact values and say, well, that's familiar because I know that sine of 45 is equal to 1 over root 2. However, the right-hand side is negative. What that tells us is we're going to be looking at solutions in the negative quadrants for sine. Okay, so sine is positive in 1 and 2, and it's negative in quadrants 3 and 4. What this tells us is our solutions are going to be 45 degrees in quadrant 3 and 45 degrees in quadrant 4. Okay, so we're going to be doing 180 plus 45 in quadrant 3. In quadrant 4, once again, we're going to do 360 take away 45. Gets us our two answers of 225 and 315. All right, if you put sine of 225 or sine of 315 into your calculator, you'll get the same answer, and it'll be a decimal approximation for -1 over root 2. All right, so there's how we figure out our solutions. We figure out which angle we're working with, and we figure out which quadrants we're working with. Okay, so once you get the hang of it, it is typically the same thing each time, but there are a few tricks to be aware of that we're going to try and cover all of them in this video. So we're starting off with some level 1 examples, and we're going to move on to some really hard ones later in the lesson. Okay, next up we have a milder example. It looks pretty scary, but there is a nice trick to it. So we're solving for alpha in the domain of negative pi to positive pi. So from negative 180 to positive 180. The equation we are solving is tan alpha is equal to 0. Okay, so in the last example, we were solving equal to some fractions that we should recognize from our exact values. When you aren't working with fractions, if you're working with whole numbers like 0 or 1, the knowledge you need to rely on here is your knowledge of sketching. Okay? If you have a good understanding or a good idea in your mind of what sine, cos, and tan look like, questions like this can become very simple. Okay? To solve tan alpha equal to 0, we've got to close our eyes and picture our tan lines. Okay? We looked at these in lesson 1. Go back if you need a refresher, but this is what tan x looks like over the pretty large domain from -2 pi to 2 pi. Okay, so we're solving this. So we're trying to see where is this function equal to 0 from -pi to pi. So in this range here. Well, where are we 0? Where are we hitting the x-axis? We're hitting at 0, we're hitting at pi, and we're hitting at -pi. So in this domain, we have 3 solutions, and we can see them clearly if we know what tan x looks like. All right, so if you're equal to 0 or equal to 1, the easiest thing to use is your graphs, typically, especially for sine and cosine are more common questions. Okay, up next, we've got an example I'm calling medium, but it's actually pretty challenging. So medium was a bit optimistic. It's probably more of a tough one. Anyway, we've got 2 multiplied by cos 2x plus 1 is equal to 0. Now, the aspect of this question that makes it more challenging is that our angle inside of our cos function is not x, it's 2x. Okay? When you have your angle being multiplied or divided by a constant, it's going to affect your domain. So the first thing to remember here, to make this question a bit easier, is that even though the question said we're solving for x in the domain of 0 to 360, if we're analyzing 2x as a part of our cos function, we need to double this range. Okay, so simple version is if x is between 0 and 360, that means 2x is between 0 and 720. So I'm just doubling both sides, 2 times 0 and 2 times 360. Okay? Remembering this step is going to make sure you get full marks as opposed to maybe 2 out of 3. Okay? All right, now let's go ahead and solve this equation like we normally would. We're trying to get everything away from the x. So let's subtract 1 from both sides to move the -1 across. And now we'll divide both sides by 2, so we get cos of 2x is equal to -1/2. All right, so we have cos of an angle is equal to -1/2. If we are familiar with our exact values, we should know that cos of 60 is equal to 1/2. What this tells us is that our angle, which this time is 2x, is going to be 60 degrees because we've got 1/2. So our angle is 60 degrees, and we're going to be in the negative quadrants for cosine. So we'll get our unit circle back. Cosine is positive in 1 and 4, so we're going to be negative in quadrants 2 and 3. Okay, so our angle, 2x, is going to be equal to 60, but we're going to be in quadrants 2 and quadrants 3. Okay, so 2x is going to be 180 minus 60. That's in quadrant 2, just here. And in quadrant 3, we're 180 plus 60. I've written some dots here because there are actually going to be more solutions because, remember, even though x is going between 0 and 360, 2x is going between 0 and 720. So 2x is actually doing 2 laps of the unit circle. But we'll figure that out in a sec. There's a nice trick to getting your extra solutions. All right, so for this one, we get 120, and for this one, we get 240. Okay, but like I just mentioned, 2x is doubling our domain and is doing 2 laps of the unit circle. So the way we get the extra solutions is we take our first 2, which was in the first lap of the circle. We're going to take these 2 answers and we're going to add 360 to them. So 120 plus 360 is 480, and 240 plus 360 is 600. Okay, so the 120 and the 240 are in the first lap of the unit circle, and then 480 and 600 are in the second lap, which gets us up to 720. Hope that kind of makes sense. We can do more of these next week if we need to. All right, so there's our 4 solutions for 2x. So to finish off, we're just going to divide everything by 2, so we get our answer for x. So cutting these all in half, we get our 4 solutions for x, and they're all between 0 and 360, so they all work out. Okay, so if you only get your first 2 solutions, because you forget to make this change here, like I said, you're not going to be getting full marks, which is not what we want. Okay, so lots of steps, like I said, lots of stuff to try and practice and get more confident with. Let's have a go at another one. Okay, up next we have another example that I very optimistically labeled as medium, when in fact it's actually pretty tough, but let's rip into it. So we're solving root 3 tan of x divided by 2 equals 1 in our domain from 0 to 4 pi. All right, so with the last question, we had an angle of 2x, and that means we needed to take our domain, which was our x, and we needed to double it. Similar thing needs to happen here. Now our angle is being divided by 2, which means we need to take our domain and we need to cut it in half. All right, so if x is between 0 and 4 pi, it means that x divided by 2 is going to be between 0 divided by 2 and 4 pi divided by 2, which is 2 pi. And remember, 2 pi is just 360. So this is really just saying 1 lap of the unit circle. So we've kind of made the question a bit easier on ourselves. Okay, now we can solve the equation. Let's divide both sides by root 3 to get the tan by itself. So we'll get tan of x divided by 2 is equal to -1 divided by root 3. All right, now let's think about exact values. What angle usually goes with tan and gets us an answer of 1 over root 3? If you're saying 30 degrees, you are spot on. Tan 30 is 1 over root 3. Okay, we have a negative fraction, which tells us for tan theta, we're going to be in quadrants 2 and 4. Okay, so using our unit circle again, all stations to central. All right, so 30 degrees, and we're going to do 30 degrees in quadrants 2 and 4. So in quadrant 2, we subtract from 180, and in quadrant 4, we subtract from 360. All right, so we're getting our answers for our angle, which is x over 2. Okay, so 180 minus 30 turns into 150, and we get 330 just here. Okay, excellent. Now we're going to take our 2 answers, because these are for x over 2. We need to multiply everything by 2 to get just x. Okay, so we're trying to go from x over 2 to x. So we're going to double our 2 answers, which gets us 300 degrees and 660 degrees. Okay, so 150 times by 2 and 330 times by 2. Now, extra trick, like I said, because our domain was given to us in radians, the way we are expected to leave our answer is in radians. Okay, so if you leave your answer in degrees when your x was given to you in radians, you're risking not getting full marks. So to finish this question off, we need to write 300 and 660 in radians. So we whack a pi with them and divide them by 180. So now they're in radians. Now we simplify our fractions and we get 5/3 of pi, and we get 11/3 of pi. Cool, so there's our steps. So remember, the important step is changing your domain so you get the right amount of solutions. Cool. All right, up next, we're on to the spicy level of equation. We have solving for y in the domain of 0 to 360 degrees. So 1 lap of the unit circle, and we're working in degrees. We've got 4 sine squared minus 3 is equal to 0. So now instead of working with sines, we're working with sine squares, which makes things a little bit more challenging. Okay, let's solve the equation. Let's try and get the sine by itself. So we're going to add the 3 across to the right-hand side. Now we can divide both sides by 4 to get rid of the 4 multiplying. Okay, now keep in mind, we are trying to get sine y, yeah? So how are we going to get rid of sine squared? Well, usually the way we get rid of a squared in mathematics is we do a square root. And whenever we do that in an equation, what do we need to remember to do? Hopefully you are thinking plus minus. So we're going to take the square root of both sides. Okay, so the square root of sine squared is sine. Square root of 3 is square root of 3. Square root of 4 is 2. And don't forget your plus minus. Very, very important. Okay, now we need to have some exact values knowledge. So what angle is typically going with sine and giving us an answer of root 3 on 2? If you're thinking 60, that is correct. All right, so 60 degrees. The interesting thing though is that the right-hand side is both positive and negative. So in terms of our 4 quadrants, A, S, T, C, because we're positive and negative, we're going to be in all 4 quadrants. All right, so sine 60 is root 3 on 2, and because we've got a plus minus, we're going to be in all 4 quadrants. So everyone gets a turn. All right, so we have 60 in quadrant 1, 60 in quadrant 2, 60 in quadrant 3, and 60 in quadrant 4. Gets us a final answer of 60, 120, 240, and 300. Okay, cool. So the trick for this question was, if you've got a sine squared, you can get a sine by doing a square root. Just don't forget your plus minus, so you get all of your solutions. Okay, on to our second last example now, an expert level equation. We're solving x in the domain of minus 2 pi to 2 pi, so from negative 360 up to 360. Our equation is sine squared x minus 3 sine x is equal to 0. Now, last equation we had a sine squared, which we could figure out by doing a square root. This one we have a sine squared and we have a sine. So we have something squared and we have something here. The way to handle this equation is we've got to kind of take a step back and sort of see this as a quadratic equation. Okay, think of this as like x squared, take away 3x is equal to 0. Okay, the way we would solve an equation like that, very simply, is by factorizing. That's what we're going to do here. We have the front term is a sine squared, and we have 3 times sine. So we have a common factor of sine x. I'm going to factor that out the front of the expression. So we've got sine x outside of sine x take away 3 equal to 0. Now we have 2 things multiplying, giving us an answer of 0. We know from quadratic equations, this means that either piece could be 0. So either the sine x is giving us the 0, or the sine x minus 3 is the 0. All right, so if sine x minus 3 is equal to 0, if we add the 3 across, we get that sine x is equal to 3. Okay, both of these, because they aren't our magic fractions, we need to rely on, once again, our knowledge of what a sine curve looks like. So if you can do a quick scribble, or maybe you can picture it in your head if you've got a really good memory, this is what our curve of sine x looks like. All right, now when we're seeing where it's equal to something, we're looking at the height of the function, which is the y value. So first of all, where is this curve reaching a height of 3? Well, we can see pretty clearly that it's never going to do that because the height of the curve never goes above the maximum value of 1. So if you're trying to solve sine x equal to 3, this has no solutions. Okay, the curve never reaches a value of 3 unless it's being multiplied by 3, which it's not. Okay, so anything outside of 1 or minus 1 for sine x will have no solutions. Over on the left-hand side, sine x equal to 0, that's our x-intercepts, and we can see we have quite a few of those. From minus pi to 2 pi, our solutions are going to be minus 2 pi, minus pi, 0, pi, and 2 pi. Okay, so solving equal to 0 is finding your x-axis intercepts, which is right here. Of course, we should write them in radians because our domain is in radians. Okay, cool. So yeah, you can factorize using trigonometry. You can solve quadratic equations using trigonometry. And don't forget, knowing what your sketches look like can make seemingly hard questions very, very simple. Okay, on to our final example now. This is from a HSC question. It's a band 5, so it's pretty challenging. So this is a master level question. We're solving from 0 to 2 pi. Our equation is 2 sine squared x plus cos x take away 2 is equal to 0. All right, let's have a think why this one is significantly more challenging than the last one. Well, first reason is because we have a constant as well, so we have a more complicated equation. With the last one, we had a sine squared, but we also had a sine, so it already kind of looked like a quadratic equation that we could do some cool algebra with. This one, we've got a sine squared, but we've got a cos x right here. So if we had sine squared and sine, we could turn this into a quadratic equation and do some cool stuff. But because these pieces don't match, we can't do that. So we've got to be really clever, and we've got to turn one of these into a sine or a cos. The way we're going to do that is we're going to rely on our old faithful Pythagorean identity, which is sine squared plus cos squared is equal to 1. Okay, we're going to rearrange this like we've done before and say, well, this means that sine squared is equal to 1 take away cos squared. Why is that important? Well, because now we can change this sine squared in our equation to a 1 minus cos squared, and now our equation will be in terms of cos as opposed to one of each. Okay, so we're going to take our equation, we're going to change the sine squared to a 1 minus cos squared, and we're going to expand this out and simplify as best we can. Okay, so we get 2 minus 2 cos squared plus cos x minus 2 equal to 0, which is already pretty convenient because we've got a 2 at the front and we've got a minus 2 on the end, and those two are going to cancel out and leave us with minus 2 cos squared x plus cos x is equal to 0. Okay, now we're at the point where we're looking similar to the last question where we can do some factorizing and solving. Okay, so the key to this question is recognizing that these two don't match, but you can make them match by doing some clever algebra, which is why this is a band 5 question, because not many people would know to do that. Okay, now a quadratic equation is always easier when your leading term, so your squared term, is positive. So what I'm going to do now is I'm going to multiply everything by -1, makes our front term positive, makes our second term negative, and 0 is still 0. Okay, now like last time, we're going to factorize this expression because we have a common factor of cos x. So factoring cos x out the front, we get 2 cos x for our first term, minus 1 for our second term, equal to 0. Now from this line, we can get two equations. We'll get that cos x is equal to 0, or 2 cos x minus 1 is equal to 0. Okay, so there are our two equations that we just got from our bracketed terms at the end. So now cos x equal to 0, we're going to solve that using our knowledge of the cosine curve, and this right-hand one we're going to solve as an equation. So we're going to add the 1 across and then divide by 2, so we get cos x equal to a half, equal to positive a half, which is important. All right, so for the left-hand one, cos x equal to 0, if we know what the cosine curve looks like, we can see that from 0 to 2 pi, cos x is equal to 0 at pi on 2 and 3 pi on 2. So 90 degrees and 270 degrees. All right, so there's our solutions for the left-hand one for cos x equals 0. For cos equal to a half, we know that cos 60 is equal to a half. So we're going to be doing 60 degrees in the positive quadrants for cosine, which will be quadrants 1 and quadrants 4. Okay, so 60 degrees in quadrant 1 gets us a half, and 60 degrees in quadrant 4 also gets us positive a half. We'll turn these two answers into radians, and there we have our 4 solutions. So x is equal to, oh, I didn't finish it off, how lazy. X is equal to pi on 3, pi on 2, 3 pi on 2, and 5 pi on 3. Okay, so lots and lots of steps. That was a 3-mark question, which is why there's quite a lot of work to it. We may not be at this level yet, but maybe when we're doing some revision later in the topic, we can try some more tough questions like this one. Okay, thanks so much for watching that. I hope some of it made sense. We'll do some more practice later on, as I said, because it's very challenging. Here's some practice for you guys to have a go at now, and we can build upon this next week when we're back in class. Thanks heaps for watching this lesson. I'll see you guys later on.